Okay, welcome back. Next up is a segment on fundamental principles of programming languages. And I actually want to start with some history. So the first programmer was Ada Lovelace. If you've been to Ada's Technical Books here in the Capitol Hill neighborhood of Seattle, awesome bookstore, she's the one who inspired their name. So she was an English mathematician who wrote what is often considered the first computer program. It was meant to run on the device shown in this photo on the right, which is known as the analytical machine. So many consider this to be the first computer because it was able to execute the same logical operations that define today's computers, making it what's known today as Turing complete or computationally universal. And it was able to do all of this using a really rudimentary processor in the form of mechanical rotating drums with pegs. I had a small amount of internal memory in the form of wheels that could turn to different positions, and had a way to receive input in the form of little instruction cards with holes punched in them. And that's actually how Ada Lovelace wrote her computer programs for this analytical machine. The point is that these are basically the essentials that modern computers have: processors, memory, input and output devices. Of course, today's computers are more powerful and they're a little more practical. So next, I want to shift gears and talk about what makes a programming language. I want to emphasize here that we don't expect you to have any programming experience, so it's completely okay if everything here is new. We're just giving you terminology so that we can basically speak a common language this quarter. So with programming languages, there are two essential elements: syntax and semantics. So you can think of syntax basically like grammar. So for instance, in English, cat, dog, boy isn't a syntactically valid phrase because it's three nouns strung together. But cat hugs boy is because it's a noun, a verb, and a noun. So in Python, for comparison here, hi exclamation point hello isn't syntactically valid because the exclamation point doesn't serve a function that Python recognizes. Now, if you run that code, Python will give you a syntax error. On the other hand, 3 times 5, as you might expect, it's a basic calculation and it is recognized. So now semantics is a bit trickier. So it governs how a syntactically valid phrase takes on meaning. So for instance, cat hugs boy is fine syntax-wise, but it probably is not semantically valid. In other words, it doesn't make sense. You'd expect it the other way around, right? Boy hugs cat. So for comparison in Python, two objects added together like 3 and hi, it satisfies the syntax requirement of the plus operator, but not its semantic requirements. So if you run this line of code, you'll get what's known as a type error. That basically says the problem is the type of objects that you're trying to add, not that you're just trying to add 2 objects. So how do things go wrong? Well, so it turns out syntax errors are usually simple typos. And Python won't even start to run a program with syntax errors. It really helps you. With semantic errors, on the other hand, Python will actually start running the program, but it won't notice the error until it gets to that line of code, at which point it will stop running. So for instance, in this 3-line Python program here, the code will start to run. We'll set a to 3. We'll print out 3, and we'll go over these commands in more detail later, but it'll get here and then it will crash on this 3rd line because it now realizes you're trying to add 3 and hi. So now the most insidious type of error, and what's known as commonly as a bug, is when the program runs, but actually it crashes for unclear reasons, or maybe it runs forever, or perhaps it gives an answer, but the wrong answer. So as a very simple example here, a typo like typing the word jello instead of hello. That will run fine, but it's not going to print what you intended. And you might only realize it after the whole program runs. So that's this 3rd type of error, and often these types of bugs are the hardest to diagnose, as I think you'll see in this course. So you can think of programming languages in 3 categories. On one end of the spectrum is what's known as machine or assembly language, which is basically what the computer speaks. It's nearly impossible for humans to write or to understand, but it runs really fast because there's no translation needed for the computer to understand those commands. So for example, this is how you just begin to write a program that prints the word hello in assembly language. Looks pretty wild. In the middle here, though, are compiled languages, some examples being C, Fortran, and Java. They're generally very capable. They result in code that runs fast also because you actually have to put your finished code through a program called a compiler. That translates it into machine language, which then gets read and run by the program, by the computer, sorry, from start to finish. Now, the downside is that compiled languages can still be pretty tough to read and write. So for instance, here's how you'd write that hello program in the language C. Now, at the other end of the spectrum are interpreted languages like Python, R, and MATLAB. And these give you somewhat less control over the computer, though that can be a good thing because tasks like memory management are handled behind the scenes for you. And they're what's known as expressive, which means their syntax is closer to English, as you can see in this really simple hello program here. So with interpreted languages, you run your code, and then line by line, it gets translated on the fly into machine language by what's known as an interpreter. So there's some major differences between these languages, and hopefully you can start to see now why we've chosen a high-level interpreted language like Python for this course. It's just a lot easier to work with. That's it for this segment, and we will be back soon.